Welcome to The Explainer. Today, we're diving straight into the fascinating story of the measurement misfits. These are units that literally confused the scientific world for decades. We're going to look at exactly how we measure the angles of our universe and, well, why some of our absolute most important mathematical tools originally had absolutely no home.
Imagine trying to sort your laundry, right? But one item has no color, no fabric, and takes up zero physical space. Where exactly do you put it? That is precisely the headache scientists faced. How do we categorize a measurement that clearly exists, is incredibly useful, but entirely lacks physical mass or length? It's a puzzle that actually forced the International System of Units to create an entirely new, almost secret club for a while.
To understand why this was such a massive headache, you got to look at the rigid clubs of the International System of Units, or SI for short. So first up, we have our base units. Think of these as the physical foundation of the whole shebang. We're talking the meter for length, the kilogram for mass, the second for time. Then we have derived units, which are basically just combinations of those base units. Think velocity, which is meters per second, or force. Historically, everything in science was supposed to fit perfectly into one of these two boxes, but our two measurement misfits completely failed to fit in.
Section 1. Radians, the 2D angle.
So the radian, abbreviated as rad, is a purely 2D plane angle metric. It's the unit we use every single time we draw a circle or measure its internal angles. Now, you probably remember from geometry class that a full circle equals 2 pi radians. But here was the big problem for scientists. Measuring a plane angle is essentially just measuring a ratio of two lengths. Because of that, the lengths essentially cancel each other out, leaving the radian with absolutely no physical dimensions. Crazy, right?
Section 2. Going in 3D style, the stereodynion. But as we know, our universe isn't just made of flat circles. Enter the stereodynion, abbreviated as SR. I really want you to push your imagination here, to expand out of that flat circle and into three-dimensional solid geometries. The stereodynion is used to measure what we call solid angles. These are angles functioning entirely within a 3D space. So, if a radian maps a slice of a flat pie, a stereodynion maps a patch on the surface of a three-dimensional sphere. We are doing this completely in 3D style.
To make this abstract 3D concept instantly relatable, let's look at a really vivid example straight from our source material. Think of a solid angle like the spread of light from a source. Just picture turning on a flashlight in a pitch-black room. You know that cone of light spreading out from the bulb, expanding as it travels across the room? Well, the size of that three-dimensional spread is measured in steradians. It's an absolutely crucial measurement for things like lighting design, astronomy, and 3D computer graphics.
Section 3. Why call them supplementary?
Okay, so if both the radian and steradian are so vital to navigating our physical world, why on earth were they banished to a category called supplementary units? Let's break down the core paradox here. Originally, the folks organizing our scientific systems isolated them because, well, they are entirely dimensionless. Because they're just mathematical ratios, they lack physical dimensions like length, time, or mass. Yet, and here is the kicker, they still describe incredibly important geometric quantities. You literally cannot calculate the spread of a 3D flashlight beam or design a wheel without them. They were essential, but they broke the fundamental rules of physical measurement.
Section 4. The modern SI resolution.
Eventually, the SI system had to simplify everything. In the past, the radian and steradian were isolated, kind of stuck with that awkward supplementary units title. Honestly, it was like guests sitting at the kids' table at a wedding. But in the present day, they've been officially stripped of that title. The scientific community finally brought them back into the main fold, recognizing them simply as derived units with no dimensions. It's a bit of a bureaucratic compromise, sure, but it finally honors their unique mathematical nature while giving our misfits a proper home.
Which brings us to a really fascinating thought to leave you with today. We rely entirely on these dimensionless concepts, the flat radian and the stereoradian in 3D style, to navigate, design, and build our physical world. So if our core measurements for angles are essentially invisible mathematical ratios, totally lacking any physical mass or length, what other invisible geometries shape our understanding of the universe? Keep your eyes open next time you turn on a flashlight. I'll catch you on the next